All right. Well, for people watching on Twitch, we are about to try and do a live experiment with Wolfram language. We're here at our Wolfram Summer School, and I just messed this up. And there are a whole bunch of people here who hopefully will help us to do a better live experiment. Okay, so the objective here is the following. I have a friend who's interested in making virtual worlds and wants a demo of a completely procedurally created virtual world made with a 3D cellular automaton. And so our challenge for this evening is to find a really interesting 3D cellular automaton that that can be run in a virtual world as a simulation where you can kind of poke at cells in it and it will do interesting things. So, I mean, think in 2D, Game of Life might be okay. There are better 2D cellular automata. Our challenge is to find something really interesting in 3D where kind of you're living in this complicated cavern with lots of stalactites and stalagmites or something like that. And the thing is kind of wobbling around and doing things. Okay, that's our challenge. So oh my gosh, why is this moving? So let's just get some idea of what we're talking about. So we can make a cellular automaton here. Let's make a typical simple cellular automaton. Let me see. One of the ones I like is, let's see, 357, 3, 1. I think it's this. This should be a cellular automaton with 3 colors, a totalistic cellular automaton with 3 colors. Let's do 500 cells there, 400 there. Let's make an array plot. If I'm right, this will make kind of an interesting pattern. Yes, there we go. So this is an example of a class 4 cellular automaton with fairly elaborate behavior. Let's run it for 1,000. Let's run it 1,000 cells across and 800 cells down. So that's something which makes reasonably complicated behavior. We can imagine kind of the 3D version of this might be pretty interesting. Let me just save this. Okay, so and let's try and take a look. Let's just sample around this cellular automaton at a few others that are in sort of the same class, just to get a sense of what kinds of things are out there. Let's not maybe do it quite such a large size. Let's do 500 by 300 here, and let's just sample numbers n. Let's say from n equals. Let's say n equals 300 to n equals 400. So let's just see what that looks like. And maybe just in order, if one of these happens to be good, let's put in a plot label so we don't lose the thing. Okay, so this should now generate, okay, so here are all kinds of different things that happen in these different cellular automata, okay? So some of remember, these are 1D cellular automata, and what we're going to be looking for is a 3D cellular automaton. So we can see something like this, where there are kind of patches of stuff going on. That might get interesting in 3D, I'm not sure. My guess is there's sort of too much stuff. There's our 357 there. Okay, here's one that might be interesting in 3D. Something like that, maybe, not sure. But our challenge is to find something interesting in 3D, okay? All right, so let's start off actually getting up a 3D cellular automaton, and then let's go from there. Okay, I think I have, let's just go figure out how to create a 3D cellular automaton. Okay, here's the cellular automaton documentation. And let's say scope, multidimensional rules specified by associations. I think this is the relevant thing. And let's take a look at this. So actually, let's take a look at this. Well, let's take a look at this guy. Okay, so what this should be is a 3D cellular automaton. That's a particular step in the evolution of a 3D cellular automaton. Okay, So that was step 6. So just for fun, let's try step 7 in the evolution of the same cellular automaton. Okay, so that filled in kind of Rubik's Cube style. And unfortunately, you know, one of the problems with 3D stuff is that it's hard to know what's going on because we can't see inside it very easily. I mean, we can change the transfer function for this 3D image. We can try doing that. Anybody know how to do this in an interesting way? So this is going to change the transfer function, and we can, I don't know what we can do here. Let's make it, let's make it so that the darkest section, why is this doing that? Okay, the darkest section is not as dark. Why is this? Something weird is happening with respect to the various kinds of streaming and so on that I'm doing. Okay, so let's apply that. So that now will apply a transfer function which causes us to be able to see inside, and now it's hard to see what's going on. Let's just try seeing what happens if we go instead of 7 steps. Oops, that's not what I wanted. And my mouse is starting to not track properly, which is a really bad sign. I wonder why that's happening. Okay, so let's try here. Let's try this. Let's just try this at 8 steps, for example. Okay, it's starting to get ears again. Let's try it at 12 steps, and I may regret this, but let's see how many. Okay, so there we've got the result of using that 3D cellular automaton for 12 steps. Now, the problem is going to be if we are just generating, so we can generate a whole bunch of different cellular automata here, but it's going to be hard to tell what's going on in them. And my guess is that our best bet is to take some kind of, well, maybe a 1D slice, maybe a 2D slice through this thing. Let's see what happens if we take a 2D slice, but have it be the case that as we're looking, you know, let's say we take the center slice, and then we look, have things that are going into the distance be dimmer and dimmer, okay? We can try that, and let's just to give us a way of getting an indication of what's happening in this thing. So for this, we're going to have a. So let's just get. So this is a 12 by 12 by 12 cube. So let's say CA data is this. That will be a 12 by 12 by 12 cube of data. And now what we want to do is probably to take the center of that cube. So what we want to do is we want to take that, and we want to take the 6 pieces of this, and then we want to take that and each successive row. Well, if I just take CA data of 6 and then I just say array plot that, I should get slice 6. There we go. So that's slice 6 inside the thing. So if I were to do that, if I were to make a table here of those array plots, I will see the successive slices in this guy. So let's say I go from, well, I could even just go from 1 to 12. Actually, I think it goes more than 12. So let's try. It's probably going 24. So let's try. Well, let's just try up to 12. Okay. So there's what we get in those. That's taking apart this 3D object. Okay. I think, actually, you know what I'm going to do here? I'm going to put in meshes in here because I have a feeling that some of these are auto-scaled to what we don't want. Oh no, they're all the same size. Okay, that's cool. All right, so then, and I think, let's get rid of the mesh. And what should be the case, I think a 12-step cellular automaton will probably go 24 things down, or maybe even 25. So it should be symmetrical. Yeah, it's going to be 25. So okay, and let's say for each of these, let's say image size to small. That wasn't very small. Well, okay, let's say image size to tiny, just so we see a bunch of them. Or anybody got okay, let's just say image size tiny. Okay, so there are the slices through our 3D CA. Okay, so as our indicator of what's going on, I'm suggesting that, I mean, if you're inside here, you can't see very far. That's one of the issues. You're just stuck in a room somewhere. And so now the question is, how do we open it out a bit more? And we're going to need something which has, and so to get an indication of that, my suggestion is that we go to the middle of this and then and then as you see further depth, well, what's the right way to do it? We show the things which are at that depth, and then we show things which are at deeper depths. So what we want to do is we want to take the stack of things, and how do we take a stack of 2D arrays, and we want the successive things in the 2D array to be added in, but with a progressively smaller. So I think what we do is we say fold list. No, actually we just say fold, and then each successive one is going to be with a slightly smaller. So I think what we want to do is we want to say the original one plus, let's say, 0.2 times the next one, I claim. And so then we want to do that with take CA data, and then we want to say the last 12 of those. Okay, I don't know if this is going to be right, but let's try it anyway. So that should give us, and then I say array plot of that. So that should give us something. Well, okay, that was encouraging. Okay, so let's test whether we actually know what we're talking about. Let's make a manipulate where we can change that parameter, that opacity parameter from, let's say, 0 to 1. Okay, so at 0, we should be seeing just one row, one slice depth. As we increase there, yeah, this is pretty encouraging. Okay, and as well, I don't quite understand why. Oh, I see. That's the average. That's when every depth is weighted the same. So here, the deeper you are, the lighter you're going to be, right? And if you occur at a nearby thing, okay. So I think this is basically right. So we can see what it's going to be. So let's say if we say a equals 0.1, for example, which is what we tried first. This is going to give us a reasonable indication of what. Okay, so a of 0.1 here, and this thing. Okay, great. So this is our indicator of what's going on. Okay, so let's try now some different rules, and let's. Okay, so what we've got here. I think. Okay, so what this meant, what this thing here means is, I'm taking a rule where around every cell there are 27 neighbors. So it's a cube, it's a small cube within a big cube, right? So that means that every, and what it's doing is it's saying grow, add a cell if there's either one or if there's just exactly one neighbor. So let's do this. If I do this, then I have to take. Okay, so I'm going to make a function here to say, you know, CA slice plot. Whoops, CA slice plot of data is this thing here. Actually, what I want to do here is let's do this. Let's say floor minus floor of length of data over 2. So that will get us halfway through the thing. And so now I say CA slice plot of this, and okay, it's a big mess, right? But that's filled in more stuff. So it's sort of unsurprising that the thing is getting denser. So this is showing. So let's imagine that if I try this, where it grows only if there are 2 things there, it's not going to grow at all. It's just going to be blank. Yeah, it's just going to be blank if there's just a single 1 in the middle. So I have to actually make a larger array of stuff. So this is the initial condition, which is right now just a single 1 in the center of. So I wonder what we have to do. We have to probably make an array. So this should be an array of 1s that is a 2 by 2 by 2 array of 1s, I think. Okay, and that, I think actually let me just check what that would be like. So a 1 by 1 by 1 array of 1s is just that, and this thing here has one extra level of brace because it's trying to sample just one. Okay, so let's try this. So if this is going to be a 2 by 2 by 2 array of ones, and for some reason something has gone wrong here. Oh, I have to have perhaps another brace. No, maybe I don't need that. Let's just try this. Okay, that seemed to work. Okay, so that's now a 2 by 2 by 2 array of ones inside this thing. And I think it would be useful to take a look at what this looks like in 3D, because I don't really understand what that's doing there. So let's take the 3D version of that. Okay, oh wow. Okay. Well now, what happens if you go inside there? How do I go inside? I think I can, how do I go inside? Oh, there we go. I wonder whether to go inside, I wonder whether I can, let's see, this is a 3D image. I wonder whether I can go inside a 3D image. Alternative would be, instead of an image, I could try something different. Instead of an image, I could say, make a 3D graphic where this is a cuboid at the position, a cuboid centered at the position of every one in the cellular automaton. So let's see here. That's the cuboid, that's the graphics 3D, and that's a fail. Let's see what happened there. Well, let's see what happens if I just say this. Maybe that didn't work. There we go. Okay, so there's the thing as a 3D cuboid. Now we can change the opacity of those cuboids, or we can probably make a viewpoint which is actually inside the object. Okay, so how do we do that? We would say, if we go here, we can just say viewpoint arrow. Well, let's just say 1, 1, 1. I don't know where that will be. No, that's not inside the object. How do I get inside the object? Well, let's try just 0.1 times that. Yes, now we are inside the object. Okay, there we go. Okay. This is super confusing, but we are inside. What, from Interstellar movie? Yeah. Okay, well let's try moving out a little bit. See whether that's more promising there. Well, it's kind of cool. Okay. It's really hard to tell what's going on with things like this. Okay, there we go. And so now, okay. I think, okay, how do I move? Yeah, there we go. So if I move out, where are we? I mean, the main point is we're in a cavern inside this object. Ugh, we hit some. Okay. Now, I mean, we could, okay, so if we really want to live dangerously, we can try exporting this to Unity and see if it's exciting more. I don't think it's going to be any more exciting in Unity than it is here. I think we're just going to be living inside this cavern. What we could do, which will take a lot more CPU effort on this little computer, is to change the opacity. Let's see what happens. If I say style those cuboids with opacity, let's say 0.4 or something, then what should happen here is we should be able to see, okay, oh, that wasn't so bad. Oh, wow. Okay. So now we're inside this glass city somewhere. Why isn't this making it bigger? Actually, you know what? I'm going to do something here. I'm going to say, okay. So now we're inside the glass city and it's not moving. Help, why isn't it moving? And my mouse is, yeah, okay. Famous last words that this was going to be easier. I thought this was going to take a lot of CPU effort because now that it's opaque, you can see through to every part of the structure. So, and we can see down here, down in this corner here, that you can see kind of many layers of the structure. Yeah, okay. Well, this wasn't so helpful. Yeah, definitely not so helpful. Help. Well, let's see. Come on. Now come on. The problem is that that rendering on this little computer. I don't even know if this computer has a GPU. Does the? Okay. Well, we can export this to Unity and see whether. Well, I don't know how to do the opacity necessarily in Unity. I'm not even sure. We can export it to Unity, see what happens there. But I think we're better off. We can see that this thing is fairly filled in. We want something which is where it's kind of like the construction of a space station or something, where it's okay. Come on, wake up here. Oh, come on. Well, I thought this might not be a good idea. That let me just okay. Let me try. Okay. Come on, we need to. I don't know quite what I did to this. If I click here and press delete, maybe that will do something useful. For some reason I managed to kill. Why isn't it working? So, anybody got any good ideas how to? The problem is that I've now made it so that this part of the notebook, well, that might work there. Come on, delete. Great. That deleted. Good. Okay, we're now back in. Okay, so that was not a very good idea. Okay, so what's happened here is, if we look back at this, so this indicator, I mean, that's the sort of indicator picture. That's what it actually looks like inside. Okay, so it's got some kind of cathedral-y thing inside there, but it's still, and now what we want to do, well, let's try, I mean, we can try exporting this. Let's try exporting this guy to Unity. So we don't want that viewpoint, and we don't want that, yeah, okay, we don't want that viewpoint there. We just want this. And now, okay, so we have this structure. Now the question is, can we export that structure to Unity? Okay. Now, in order to export anything to Unity, I have to use this weird unreleased version. So let's try it here. And if anybody wants to play with this one, let me send this in our internal chat here. That wasn't a good idea. Insert code, internal chat, press send. Oh, it's sent. That was good. Okay, now let's try doing this in Unity. So what should happen here is it should say create Unity scene should create an empty space. It says here. So let's try that. If it says, so we say create Unity scene. See what happens. Well, Unity isn't running, which is a really bad sign here. Let's kill this. Maybe it can't even be killed. Let's quit here. Let me start Unity first. Okay, started Unity. Now let's try creating Unity scene. I know what's wrong. I need to tell it. Okay, I need to say here that it needs, and I should also make this a little bigger. Something is strangely wrong with the mouse here. Let's make this bigger. Now I need to say needs Unity link. And now I should be able to say create Unity scene, and I can't. I wonder why I can't say that. Let me see. Create Unity scene says create an empty space, but let's say let me see. Well, create Unity game object. There's a Unity open. Let's see what happens if I just say Unity open. Ah, that's encouraging. Okay, so something is opening here. But why isn't that opening? If I just press new here, new Unity project, create project. Okay, this might be working. Okay, so far so good. All right, well, okay, so that might be a new Unity project. So now let's go, I don't need ads there. Now let's go and try and send this thing. Let's recreate that thing and send it to, by saying create Unity game object. Let's just call it thing. There it is. Now let's see what happens. Oh. Well, that wasn't a good sign. What's that? Well, yeah, but I think there's got to be a better way to do it. Let's let me just try doing this. Or I wonder whether we can make a mesh. Anybody know how to make a mesh? Hey, Christopher, do you know how to make a mesh? Do you know how to make a mesh out of cuboids? Okay, so let's just try making an image mesh from this. Oh, right. Why is oh, there's a comma 1 there because it had a... Okay, oh, that's cool. All right. Okay, that probably isn't going to hurt anything. Okay. Okay, so now let's take this object here, that image mesh object, and let's try sending that to Unity. It's thinking, it's thinking. It's got a lot of cuboids to send. I wonder how it's doing it. I think each one has to be created using a .NET call inside Unity. What? Oh, yeah. Right, but if it's a separate cuboids, each one has to have its own ID. I wonder what will happen if I kill it, whether it will make the link get messed up. Well, so I can't kill it. Okay. You know what? I think what I'm going to do, I think I am going to kill it, and I'm going to kill off the Unity instance. Yeah, this is really kind of dead. All right, let's kill this off. Now it killed that. Yeah, that's good. It killed the parent object in Unity. That's a good sign. So now let's rerun this. Needs Unity link. Now let's say Unity open. Okay, that's making one of these. That's good. Now I think I pressed open. I pressed new before, right? Inside this Unity creator thing. And I said create project. And it created a project here. That's good. And now what I want to do is make a much smaller object and see whether we can export that. So instead of running it for 12 steps, let me just run it for 4 steps. Okay, now we've got a thing like this, and now let's try exporting that to Unity. Maybe I should, oh, there we go. Okay, thing. Oh, there we are. Here we are. Here's our thing. Okay, now I just have to know how to use Unity. Okay, there we go. So there's the thing. And now, hopefully, I can go inside the thing. I'm not sure this is any much more helpful than what we already had. But, yeah, so there we are inside the thing in Unity. Now, okay, so this thing is not a winner as far as kind of I don't think this thing is very much of a winner as far as a habitable object in the virtual world. Not exciting. So let's go back and explore some more rules, and then we'll push those into Unity and see what they look like. So remember our indicator up here looked like this for this guy. So let's just see what happens if we use a different, if we try doing it with, let's say, only 3. Okay, we don't get anything. 3 or 1. It's really hard to tell what's going on from these pictures. Really hard to tell. I mean, I think if we do the 3 and 1 thing here, my prediction is it's going to just be it's going to be a mess. Well, yeah, it's just very filled in. So I think what we want to do, this is something where what's happening is it's saying if 3 or 1 cells in a 27-cell neighborhood are 1, then grow. So we can make it a little bit more elaborate by saying that there are cases in which it either grows or it dies off. So we can try those. And let me see how we do that. So let's go to Cellular Automaton again. And let's go to the documentation. And it says here, so they're growth and survival cases and growth and decay cases. So we can say, so let's say growth and survival cases. So great. Oh, that's a growth and survival. Okay, so what this says is it grows if there's 3. Okay, that wasn't very exciting. Let's say if it grows if there's 2, it survives if there's 3. That wasn't very exciting either. It survives if there's 1. Okay, that's a little bit more interesting. Okay, that's got a little bit more empty space in it. So that's, it grows if there's 2, it survives if there's 1. I think there's no way to get it to survive any less than if there's just 1. Let's see what happens if we say grows if there's 3 and survives if there's 1. We don't get any growth. I wonder if to get growth, I wonder if we can do a cube of 3 of these guys to get growth. Nope. Let's see what happens if I say growth. Nope, 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 nope. So remember what this is doing is it's saying you grow. I mean, we can do much more general rules. This is a very specific class of rules that say, you know, grow if there's, so maybe we should try a more general kind of rule where we say, let's try a general totalistic rule, which means that, so let's say, let's see, an outer totalistic code, which means, all right, let's do this. We want neighborhood 27, dimension 2, 3. Okay, so let's try this. Cellular automaton. Okay, dimension, neighborhood, blah, 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 blah. Outer totalistic code is, let's say, 1, 2, 3, 4. And let's not live that dangerously. Let's only go for 6 steps. Okay, so we have some random thing with that outer totalistic code. Let's try using our indicator here. Okay. Who can figure out what the range of values of the outer totalistic code is in the case where there are 27 neighbors? Two colors, 27 neighbors. So this should give us the slice plot for that case. Okay, so let's just try. Okay, so the outer totalistic code, the maximum value it can have is, actually if it's a totalistic code, well, outer totalistic code, the maximum value of the outside things is 26 times 2, I think. That's a very big number. It can have, because it can have for every one of the possible cases, you have to say what it does. And so that's 2 to the 56, that's 2 to the 26, 2 to the 55. I claim that's is that as much as 2 to the 55? The maximum size of the rule? Let's just try feeding in some absolutely huge value here. See whether it thinks, yeah. Yep, so there's a lot of rules. So I think there's 2 to the 55 rules to study, if I'm not wrong. So we pretty much can try any number here. We could try a random integer up to from 0 to 2 to the 55 minus 1, I think. And we probably want to actually not put it right in there, because if we find a great rule, then it will be embarrassing if we don't have, if we haven't said what it is, because we'll never be able to find it again, because there are 2 to the 55 of these guys to go through. So let's just go with RR equals this thing here. Okay, so we're going to get a whole bunch of random things here. So let's just try generating, let's make a table of 30 of these guys. Oh, okay. Oh, the maximum, how convenient. It's telling us the maximum possible rule number here. So we don't have to actually work anything out. Let's take the log base 2. What an incredible cheat. Let's take the log base 2 of that object, and it's 54. Okay, so I was off by 1. So we have a small problem there that if the thing is, this thing is failing when there's no cells that are generated. So what we want to do here is we want to say, in the CA slice plot, we want to have a special case of CA slice plot of nothing is graphics of nothing, I think. Let's try this again. Okay, so is there anything too exciting there? Nothing that exciting looking there. Let's try this again. Okay. Oh. Okay, so somebody has a suggestion. Jonathan has a suggestion here.
Yeah, it looks a little bit more interesting if you start with a random array. Not much, but...
Not a huge win, I would say. Okay, let's see what happens here. Vlad has a much more elaborate thing here. Let's try Vlad's thing. Okay, now, what on earth is this doing? Okay. Well, that's cool. Can I move around here? But you've used a different cellular automaton here. What's that? Which was the one we were using before? This one here. This one? Yeah, I think it was this one. Do you have the same initial conditions? No. Okay. Well, so okay, it's cool. Yeah, it's cool. I mean, it's interesting. I mean, I wonder whether we can get, who knows how to get Unity. Maybe if we just try and export this thing to Unity with an opacity, I bet it won't work. Okay, who knows how to, maybe somebody on Twitch knows how to set Unity to have a different opacity. If we're lucky. Okay, well, let's go back here. Okay, so far, none of these, I mean, so these are all starting, I mean, this one here is not totally terrible. This one here might be interesting. That one there is going to be some kind of thing with a bunch of points. You know, it's some kind of pointy creature, but it's not. I mean, what I was hoping is to find something very sparse. Now, we can do an automatic search for something very sparse. Let's look at what that one looks like. Oops. What that one looks like if it is, let's just look at what the actual form of that one is like. So, big what? I agree. Starting from some, okay, so hold on, let's just look at this one. Let's just get some more intuition for what this one does. Okay, so there's the code number. And okay, so that one was a little guy with little spaceships off the ends, but not a lot of, I wonder whether if we apply your nice plot thing, whether it will look interesting. Yeah. Right. I agree. It's full of cubes. Okay, so let's figure out how to make something which isn't full of cubes. So we can try, let's just try, one thing we might try is, so what we want is something where there's a large amount of white, or almost white, in here. Okay, how to get that. When in doubt, search. Let me see. Where did I define this? Here we go. So let's call this search. And then this is basically, oh gosh. Okay, so what we want to do here is search a whole bunch of rules and find ones for which the CA indicator is, so if I take a cellular automaton here, okay, so what do we think we want to do here? We think we want the total of these to be, or the mean of these to be, what do we think we want? We want as many holes as possible. Right, so how do we get that? So we've got this thing, and we want to detect its large holes. So if we take an image of that, well, that's a very small image, but there's an image. So now the question is, how do we detect large holes in that thing? So we want, we could do this with image processing, or we could do it, let's see, how would we find out where there is, again, well, you want to find big caverns inside.
So we take image 2D and make image inverse, and then here the holes will be the depth pixels. Maybe do convolution of that with image 2D.
Let's just try something here. I just want to see whether we can get up to, okay. So it doesn't take long to get up to size 20 here. So at least the cellular automaton evolution is nice and fast. Let me even try living even more dangerously. Let's see what happens. Okay, so even to size, to 30 by 30 by 30 cubes is not a big deal. So now the question is, let's do our sample of just random rules here at 30 by 30 by 30, just to see whether there's anything that looks reasonable. Let's do it to 25. All right, so any caverns that you see. So that guy might have caverns.
Is there any way to search an array for a subarray that might have a large number of zeros?
Yeah, so I think we might be able to use image components. 2D image components would search for a blob of a certain size. Maybe we can use 3D image components. I mean, see, something like that might have reasonable caverns in it. I don't really have good intuition for what the, I mean, let's try that one. That one looks like it might, I mean, it has a bunch of lightness in it. It might have caverns. We also probably should be trying them for random initial conditions. This is growing the thing, and then, I mean, it could be a lot better if we start from something big and then it's going to carve out. But I want to try that one there. copy this down.
You send the code of generating all these rows.
Yeah. Oops, oh, somebody found something there. Okay, Richard found an interesting thing. Let's take a look at this one. Growth survival cases of that. Wow. Wow. What is that? Well, it's a holy object, so to speak. That's interesting. Okay, I wonder what that does. Okay, so what did you do there? You had this be, you started it from a much larger cube, right? What's that? Yeah, no, I think so. I think that started from a much larger cube. And then what you're doing there is filling in. So let's try what happens. Let's see what happens with our indicator function. Instead of doing this, we can say CA slice plot. Not what I expected. Why did that not work? CA slice plot. Oh, it's comma 1 there. I see. Okay, so that's what it looks like if you're full of holes. And if we go, let's go 30 steps here. It fills in. It was just, so I think what happened here, at 12 steps, let's look at it first, successive steps. So at 20 steps, yeah, well, maybe it isn't. Maybe it isn't filling in. Maybe it's just that there's stuff in the distance there. We could take this guy. Let's take this guy and export it to Unity. I think there's a way of deleting a Unity game object. Let's find out. Create Unity game object. If we're lucky, there's a delete Unity game object as well. Well, let's just see whether there is one. Delete Unity game object. Okay, let's see what happens if I say delete Unity game object of thing. Something happened. Okay, so now let's say oh, this was a much, much huger one than I tried before. Let's just try 6 here or something. Oh, look at that guy. That's pretty swank. That's a pretty nice object. What an interesting looking object. Wowee. Okay. Well, let's see what happens if we go to like 10 steps here. Okay, now it's kind of fallen apart. And now let's see if we go to 15 steps. See whether it can deal with that. It's a little bit flaky, so to speak. It's got lots of little pieces there. But not totally crazy. But let's try and export this one. This one looks really kind of cool. Okay, so that's on line 6. And we want to take that and create a Unity game object called thing. See what's happening here. Okay, let's see what it's doing. Well, there's nothing there right now. Let's see if something arrives. Still running, still sending it. Come on, up, something. was sent. Da-da. There it is. Well, that looks kind of interesting. Okay. I mean, that could be a space station under construction or some such other thing. If you found that floating in space. Okay, so here's the real question. If we visit an alien planet and we find this in orbit around the alien planet, what is it? Was it made for a purpose? Was it a form of art? Was it? Did it grow like a crystal? What is it?
Home for alien babies.
What's that?
Home for alien babies.
Yes, it's a home, right? For the. Okay. Well, this isn't great, but it is at least the beginning of something halfway reasonable. But I think we should look at the case that we were. We had this thing before we got to this. We had identified one thing here, which was this one here, this 13.8 whatever it is thing. Let's take a look at that 13.8 whatever it is thing. Oh, well, okay, but it looks like inside this object, things are not as bad as they seem here. Well, we kind of know that inside the object it isn't as bad. So I wonder if we want to try and actually take that. Oh my gosh. Now we have to, I mean, we could do one of those nice plot things and go inside the object. Okay, let's try that. I'm not optimistic about this. Okay, now we're inside. Who knows? Okay, should we try exporting this one to Unity? See whether we can see what's going on in Unity. We can try that. So let's go to our little pipeline here for exporting things, and let's say there's that. So now we want to say delete Unity game object. And now this one, well, we're going many more steps. So I'd like to try just going 6 steps here. And let's try. That's not very exciting. It's much more interesting at 12 steps. So let's see what happens at 8 steps. Oh, wow. Okay. All right, so let's try sending this to Unity, create Unity game object, call it thing again. Seems to take rather a long time to push this geometry to Unity. I wonder why that is. Okay, meanwhile, let's go back over here. And let's ask the question, how do we understand where there are voids? So there are claimed to be voids inside this thing. And presumably, if we just take that thing, yeah, in fact, we can see the voids by just taking come on, turn over. Oh, that's really weird. So I don't see holes inside this thing. Maybe we're off by 1. Maybe if we go 11 steps. Oh yeah, wait a minute, there's a hole. Yeah, okay, so you can see there, inside the structure, there's kind of a way to get through. So there are holes inside the structure, but they're not exactly easy to find. Okay, so I think we need another, okay, so what we want to find, one thing to do is just find things with a very low density of ones. Just count the number of ones and see whether we can get ones with low density of ones. Okay, so that's a real simple thing to do. Let's try that. Of course, we don't just want to find the ones that have, you know, only one black cell. So we need to find, okay, so here, let's say we go 10 steps and we just get the cellular automaton out. We get RR goes to, and we just need to find the total number of ones in the structure produced by the cellular automaton. Okay, so that's that structure, that's the width, it's comma. I think there we have that, okay. Okay, so this is telling us the number of ones in the output. So for example, this guy here has only 8 ones. So most of them have like 10,000 ones in them, right? So there's a lot of stuff there. So what we're finding here, so let's go ahead and just figure out, oops. Let's go ahead and figure out across a whole bunch of these, how many, I think by the way that even numbered rules are going to be better because they at least don't have all zeros going, well, okay, let's just try 200 of these. And then let's make a histogram. Let's make a histogram of those. Okay, so what we're seeing there is there are some rules with comparatively low count. So for example, let's say let's take that collection there, and let's say let's do this. Let's say I want to take select rules with where the right-hand side, where hash sub 2 has to be greater than, let's say, 50. And then I want to take that sort of checks for the ones that have just tiny stuff. Well, let's say 20. And then let's say take largest by hash sub 2. Okay, so these are the rules that have the smallest counts. So these look like they might be kind of interesting. So let's try some of these. These are rules with small counts. I mean, I'm a little bit suspicious about that number 56, but let's just try this rule here, for example. Let's try that one, and let's get what we have to do to test it. We'll get this thing here. Oh, it's actually not one of those. Let's just get oh, come on. So I want to just get this rule with, now I want the case here where we're getting like the 56 guy here. And now this is going to mimic a slice plot of that. Well, that's really weird. That's saying, so this is in the case of, oh, that's the 24 case. Let's try. I'm really confused here. Oh, I see what's happened. this is just a tiny cuboid of cells. This really didn't grow at all. That's not interesting. So let's try one of these other rules that has a modest number of black cells, like 592 there. Okay, let's try that for a larger size. I think it's just growing very slowly. Let's try 30. Yeah, I don't think that's full of voids. I think it's just a small object. So I think what we need to do to test for that is we need to say it's got to be a big object, but it's got to have a bunch of holes inside it. So big object means that the outer boundary, so the convex hull of the object is, we want to say what's the density inside the object. Boy, let's see, how do we figure out what the size of the object is, what the maximum extent of the ones is? What's that?
They take all the positions of flux and then they calculate norm.
Yeah, that's a good idea. Well, we have to, but it has to be relative to the center. So that's kind of a nuisance. Yeah, but the origin will be off in one corner. Yeah. Yeah. So we have to take, if we take the average of all the coordinates, the average absolute value of the coordinates will give us the basic density of the object. No, that's not very good. We want to take the maximum coordinate. That will give us the answer, right? Because the maximum coordinate, all right, we should probably wrap up soon here, but maximum, the position of the ones there, let's say 10 here. Okay. So let's try one of the other rules. I see. Okay, so there is that we can get something from this. So we can write something which tests this array. Let me see. Total of flatten of array is greater than 20, and max of position in the array of 1 is greater than 20, and let's say okay, so if those things are true, then return total of flatten of array, otherwise return infinity. Okay, so I'm claiming that if we say this, so if we want to take this thing here, and then we say table of that, we're making a table of those things, 200 of those things, and then we're selecting the things in the table. No, we're not selecting, we're just taking test CA of hash 2. Right, we're testing for things. Okay, here we go. That's not right. Oh, I see. We've got a table of objects here, and we want hash 2 is, oh, I just want the cellular automaton data there. Okay. Huh, well, okay. Oh, I see what I want. Okay, I think it's probably a sign that we should be wrapping up in a moment here. Okay, so for the cellular automaton, we want to test it there, then we want to close for the width, then we want the table, then we want to say smallest by hash 2. Okay, there we go. Oh, come on. This table, let's look at this table. So this should show us, yeah, this should show us cellular automata. Oh, come on, take smallest by, better work with infinity. That would be embarrassing if it doesn't work with infinity. That would be a bug. So can we, but let's, okay, so if it really doesn't work with infinity, let's say 10 to the 10 here. I really don't think that should be necessary, but let's try that again. Okay, it did something there. Okay, so now these are rules that apparently don't have, so these are rules that have some reason to believe, we have some reason to believe might be interesting. So let's take a slice plot here, and we're kind of on a hunt now. So that's a rule which has only 600. Oh, okay. Well, okay, so that's an example of something with decent extent. It has arms that reach out. So that's what we get if we ask for things that have decent extent, but not a lot of, so really that's finding its low density, not by having you see, these are finding their low density, not by having holes in the middle, but by reaching out with arms. So, I mean, most likely we should be starting with random initial conditions. The problem with doing that is just it's a bigger search space because we also have to search different kinds of initial conditions. But I would say that these are, so let's just do one more search here so I wonder how we would detect the presence of arms. We'd probably go out in all directions and we'd ask whether the thing, but let's try looking at the 1,000. Let's try getting the 10 best from, actually probably we don't want just 10 best, but okay, we'll do these. And so now here, okay, so these are the ones that came out. Well, that's kind of cool. Those ones have little cuspy type things in them. But fundamentally, all the ones that are quotes low density are low density because they have because they have arms that stick out a long way. Now, those might be interesting if we start them off from random initial conditions, but we really want something where the sampling of space is fairly uniform, but yet there are big holes in the middle. Well, let me see. Let's try. You know, we could try these very rules with random initial conditions. I'm going to do that. So to get random initial conditions, I just have to replace this. That was extremely unexciting. Okay. Well, anybody have anything? Oh, look, somebody sent something really cool here. Let's see, we got a bunch of different things here. Okay, so is this the one? It's good to send these things as actual code, but let's see what there is here. This is, I should have been watching this chat stream. Okay, what's this? So this is now, well, that's interesting. Is that just because it started off? Oh, that's a rule that we were using before, but it just started from a big cuboid, and it's just carving out holes in the big cuboid. So I guess that's a pretty common thing to find. I mean, these are nice structures. My gosh, these would be cool in your average orbiting thingy. Okay, who has other stuff? Anybody else got things that they can send on the chat? This is our first actual use of this code chat thing, so it's nice to see that something's working. Is anybody watching the Twitch stream? Does anybody on Twitch care about anything here? Any suggestions from the Twitch world?
You're just blowing their minds. They're amazed at all of these.
Okay. Well, let's gosh. Okay. Okay. The main point here is let's yeah. Don't let me distract people, because if you're going to come up with great code here, I'm going to keep talking, because otherwise we're going to people who are on Twitch will I want to figure out how to get a better way of finding holes in these structures, and I'm kind of thinking 3D image processing may be the right way to go. So in a 2D image processing, we want to find, I think if we're finding blobs, Okay, let's try it. All right, so Vlad's idea here is that we would take one of these objects. Let's see what our favorite object is. Well, we could take, I suppose we could take this object here if we want to, and we could take this thing and we take that object, we take image 3D, now we blur it by a bunch of, let's blur this by how many? By like 4 cells or something. Okay, it's a big blurred mess there. It's kind of cool that we can do that. Actually, really cool we can do that. Now let's take this and let's edge detect. Are you suggesting edge detecting this?
I'm suggesting doing the gradient filter.
What's the difference between a gradient filter and edge detection?
After we have a gradient filter, we can just sum everything up.
Okay, well, I want to see what happens if we do edge detect anyway. Okay, so if we edge detect, it's kind of cool what we can get here. So that's the edge detection of the blurred object, which is a bit like the previous thing. Okay, if we're going to do this what's it filter, the gradient filter, Vlad has to pay attention because Vlad has to tell me what gradient filter to use. Okay, so let's get that thing, and now I got to look up gradient filter because I don't know how to use these. Let's see, gradient filter. Any ideas?
The other point is the place where one color changes to the other color rapidly.
Okay, well, but that's an edge detection basically. But I mean, we can try gradient filter of this thing.
We need to do image adjust on it. Otherwise, we see something.
Okay, well, let's try, okay, this image adjust. Okay, what's that showing us? It's cool, but what does it show us?
Shows us that we have to something greater than 2. Maybe 10 or 15 in order to
So you're suggesting in the blur.
do 15, remember?
Okay, so hold on. So let's get our original data. Let's blur it by what? By 15 cells?
Yes.
Okay. And then let's gradient filter that thing. By what? By 15 cells again? And then image adjust the result? Okay. It's cool. What does it mean?
There's a bunch of white stuff at the borders. And if we sum everything up, just calculate the total of that, and this will be our measure. Goodness, how good the cellular teams are.
Okay, so we think this thing, if we take image data of this, that will give us, so image data of that.
But without image adjust.
Okay.
Image adjust is adjusting for us to make it.
Okay, all right, let's get rid of image adjust. Okay, so this should be a bunch of numbers. Great, that's not very many numbers. But okay, let's just do, well, I was just going to take the first 2 things here just so we see what there is. Okay, so these are small numbers, so we can certainly do the total of the whole. You want the total of all the numbers here. Is that right? Okay. What does that number mean?
Some kind of quality of the cellular automata. And what we want to have is we want to have this maximum.
Maximum?
Yes, as much as possible.
Okay. Well, we can try it. All right, so let's try sampling. Okay, well, here goes then. Let's try. Okay, but we don't want to have. Let's go back to our big study up here. I mean, these are cool pictures for sure. hold on. Let's see, this wants to be RR. And now, let's do this. Okay, so what you want to do, let's sample it with 100 of these. Well, let's just sample it with 10 of these, and let's just take 3 of them, and you want to take largest by, right? Okay, so those are the values, those are the largest values we get there. So these are, so let's take a look at one of these rules and see what it actually does. And let's look at the slice plot. We could just look at this thing, or we could look at the slice plot. Let's look at the slice plot. There's a rule. Blah. I mean, we can see what this thing, let's look at what this thing does in the full graphics 3D thing. Because I have a feeling, I think there's a weird thing with those corners there. I see a bunch of corners. I see those corners in, I mean, of course, we tested it on 10, and we're now running it on 30. Oh my gosh, it may be. Okay, let's just try, let's try 20 here. Whoops. And we killed it. Okay, we have to restart that. Okay, let's go down to the bottom and find that thing again. Hopefully we saved it fairly recently. What's that? Oh no, we didn't save all those lovely blurs and things. Let's redo those, because I don't want to lose those. Those were really cool. I thought I saved those. Well, I'll tell you what, let's actually start a new notebook here, so that we don't save everything in the same giant notebook. Because I bet that thing was already a gigabyte or something with all of that graphics in it. So let's try this. And let's try graphics 3D, cuboid, position, that, comma 1. Oops. Oh, what did I do wrong? Position. Oh, I have to map the cuboid. Okay, good. All right, now let's just make sure. Okay, this was 3D CA search 02. Okay, so now what we were doing before was we were taking this and we said blur that by like 2 or 4, let's say. Oops, blur the image 3D of that. No, we don't need that. We just need that. There we go. There's the blur of the image 3D. And now the first thing we did there was to say edge detect that. And that just gave us something back that was like the previous thing. Then we said gradient filter. So having blurred it, let's see, we had that there. And then we said blur that by, let's say, 10. And then let's take gradient filter by 10. And then image adjust that result. Okay, now we have those things again. So that's cool. But now your actual criterion was take that gradient filter without the image adjustment and take the total of the image data of that gradient filter, and then that will be depth 3. No, we're good. I mean, what do you want to do? No, that's showing you the total, that's showing you the measure. That's the total there. And now what we were doing before was we were doing that selection, this take largest by, this thing here. So let's do that again over here. So this was take largest by. And then here, instead of this weird test CA thing, what we want to do is this whole thing here, total CA. And then at the end here, we want to say, after that, we're going to say for the cellular automaton, now we close for the image 3D, then for the blur we give a 10, then for the other one we give a 10. Okay, we give 10 for blur, 10 for that, then that's the gradient filter. Oh, you're saying why do we need another image 3D? Yeah, we don't need another image 3D, that's completely unnecessary. There, that. Oh no, what I have here, oh gosh, I meant image data there. And we get the same result. So for some reason, total, I guess total must work on, doesn't really matter, it doesn't care. Total probably doesn't care whether it's operating on a 3D image or whether it's operating on this. Okay, so now we have total of image data of all that. And now we've got, we close for the width. We'll do it for 100 of these things. This time we'll save it. Oh, come on. Okay, let's figure out what we did wrong. So this cellular automaton is, we make an image 3D of that cellular automaton. Oh, I see what went wrong. The image 3D, sometimes the cellular automaton gives nothing, gives a null object. And I bet image 3D doesn't like being given a null object. That's actually arguably a bug. Yeah, that's a bug. I think image 3D should be happy with that, but we can deal with this. We can just say if depth, well, if the thing is a null thing like this,
I think if you replace that with rapid speed, it would still show you the I don't know if that changes.
no, I mean, no, we don't want to, yeah, I understand, but this is what we need. The problem is that the thing that's analyzing all the blurring and so on is going wrong. So let's see whether this thing is able to deal with a okay, well, it's not very impressive of the thing. Okay, well, so we can do that. We can replace it with a single 0. If it's equal to this, then make it a single 0. Otherwise, make it the ordinary thing. Apply that to the cellular automaton. Apply that pure function to the cellular automaton thing. Okay, now let's try running it. Ta-da! See what happens. Oh, come on. It's not a real valued vector. Ah, silly me. Okay, I should have put a comma 3 there. Now let's try it again. Come on. There we go. Okay, so there are our winners in the, so now we can try this again for our winners in the other notebook. We can try, let's try that winner there, and let's see what it looks like. Okay, uninspiring so far. Let's try looking inside. I think there's a way to actually do the looking inside. Okay, so let's say, take that thing. You know what? Well, column minus 12. Okay. Ta-da, let's turn it around. Well, it has there's no real way to escape in here. It's not very escapable. So I don't think, I'm not convinced. Glad I'm not convinced. Look at this thing. I mean, we can make it bigger. Let's try making it bigger. No, I'm sorry. There's just, this is way too filled in. So what went wrong?
If you average cells with some neighborhood and then filter out, make holes in it.
Okay, so you're suggesting running another cellular automaton, basically, to figure out whether it has holes.
Well, I mean, just like just apply it to the cellular automata and have interesting, make bigger holes.
Yeah, I understand. Yeah. I think it's probably time to wrap up for today. I think we've made some decent progress here. I mean, we've got, there's clearly more work to be done, but and we could do with a more powerful computer. I should use this. My computer at home is much more powerful than this, and it will be considerably zippier. It also would help when we do these tables. Actually, I should have been doing that even here. This machine probably has 2 CPUs. The machine I have at home has 12 CPUs. And I can easily put in 1,000 CPUs, and it would be easy to, it will work on, anytime we do a table here, we should be doing a parallel table, because that way it'll just send the thing off to compute in parallel. And then if we got a reasonable criterion here, we can then do a big search of 3D cellular automata and try and find one that has, again, we don't completely know the criteria. I mean, the criteria appear to be lots of empty spaces in the middle. Exactly what? I mean, that's really what a class 4 rule, of the type that we were looking at the very top here. That's kind of the story of a class 4 rule. Is there's lots of wherever it was, the very top. If the notebook will even scroll there, the story of something like that is there's a lot of space in there. And so now notice that one was started off from random initial conditions. What we need is the corresponding thing for from random initial conditions in 3D, we make something like this, and that's what we have to do. Maybe we can return to this. Actually, what we should do is maybe we can return to this at some later point, and at least we can have one virtual reality set up. So at least one person can see what this looks like if you wander around. Because I have a feeling this, if we can load this Unity geometry into the VR system, I don't know what that one was. That one was, let's see whether that was not a very exciting one. Maybe it was. Oh, I see. We're inside this guy now. Well, that's sort of interesting. It's a little weird. I don't know quite what's going on. It looked like some of the geometry got messed up here. We've got only one side of some cuboids here. But in any case, I think this might be more fun to look at in VR than it is in just on a screen here. It's not so. I wonder how one does that. It's a good question, how one can do that. That's something that I don't know whether the world is modern enough yet to let the Twitch audience see stuff. If they have their own Vive systems or something, their own VR systems, whether they can see the thing in VR from somehow through this Twitch stream. That would be fun if it was true. Don't know if it is. All right, let's wrap it up for now. So goodbye, Twitch folk.